Okay, so now we're going to start talking about, we're going to keep talking about storing carbon in forests, and in particular, a policy for incentivizing forest owners to store more carbon. And I'm going to call this a carbon incentive and fee approach. We're going to focus on a single stand, once again. But by the end, we'll zoom out and kind of think about what's the landscape scale effect. Well, we're going to think about this in our classic amenities setting. So here's our net present value of putting a piece of land, a single stand, into a forestry rotation at some constant rotation length, capital T. And A capital T is going to represent the net present value of a stream of amenity values. So remember that so far we've defined A capital T as the sum from time 0 to the end of the rotation of some constant or possibly changing stream of amenity benefits or costs, as the case may be. Okay, so now we're going to try to think about how do we want to specify this equation for this particular carbon incentive and fee setting. So we want to pay a carbon price V, little v, for every additional ton of carbon stored in this forest stand. So we need to define how much carbon is being stored in the stand. And we're going to say that for a given time t, the amount of carbon stored in the stand is just a linear function of the timber volume. So this is our timber volume equation, also as a function of time t, and we're just going to multiply it by some constant psi. And that's going to give us the amount of carbon that we have in the stand. That's an oversimplification of how you would actually have to calculate the amount of carbon, but it's not too bad of a simplification. So in each time step, little t, the amount of new carbon that we're adding to this stand is just the derivative of our carbon function with respect to t. That's telling us this, the tiny change in carbon given some small instantaneous change in time. That's our derivative. And so it's just going to be our constant psi times the derivative of our timber volume function. Okay, that's pretty easy so far. So to represent what is the present value of all of our future carbon payments, the revenue side of our carbon payment policy, which I'm going to call A little r cap T, is the integral from 0 to cap T of multiplying our carbon payment. So the carbon, the value that we're putting on every ton of carbon multiplied by the new carbon we're getting in each time t, and we have to discount that given where we are in the time frame. So pretty simple. All we're going to do is combine these two parameters, v and psi, into one parameter gamma to try to keep things a little bit simpler. So that's the revenue side of the carbon payments over time, over a single rotation. But we also need to make sure that the landowner is paying back for any carbon that is lost to the atmosphere again once they harvest. If we're not also charging for the carbon that gets released when they harvest, then people can game the system and just harvest, clear cut everything to just try to get back that carbon payment when they plant again. And you could have a really perverse incentive to actually lose carbon to the atmosphere rather than take more of it out of the atmosphere. So we really have to pay for the carbon that we get and charge for the carbon that we lose. So this is going to be the payment, the fee side of the policy, which I'll call A little c cap T. That's just going to equal the value of the carbon times the total amount of carbon that we lose when we harvest, which is just C at time t, or rotation length, which we defined as psi qt, discounted from the time that we have to pay it, which is when we harvest it. And so again, our gamma is just v times psi. Okay, so this one's pretty simple. We don't have to integrate anything because we know what our carbon, what amount of carbon we have by time t. We just pay it back all at once. So our total A cap t is the revenue minus the costs of the amenities. And then I just rewrote everything here. Okay, so now some of you might be thinking, well, would anyone actually want to do this? What's the point of getting all these carbon payments and then having to pay them all back again? Is that really going to do anything? And, you know, might landowners even possibly lose out if they have to pay back all of this carbon once they harvest? So we're going to look at this a little bit, and we're going to simplify that expression that we just derived to try to figure out, will this definitely be an incentive to landowners to store more carbon? So here's the equation for A cap t that we derived. To simplify it, we're going to start by integrating this first term by parts. So just to recall what that means, when we integrate by parts, we're going to define some term as u and some term as dv, and that's going to equal u times v minus the integral of v times du. So hopefully you remember this from your calculus class. It's a pretty useful tool. I end up using it weirdly a lot, so I'm just going to walk through it a little bit. So we're going to define our u term for this integral as, what did I say? The u is going to be, our discount term, and our dv is going to be our q prime t dt, so our volume derivative. I'm just going to take the gamma out here. We don't have to worry about it when we're integrating by parts because it's a constant. Okay, so now plugging this into our integrate by parts equation, we're going to have this thing is equal to u e to the negative rt times v. So we have to integrate our dv term. And integrating our qt derivative is just qt again. So that's easy. And we have to evaluate this thing from 0 to cap t because that's what our integral is doing. And then to finish off our integrating by parts, we're going to integrate from 0 to t, our v, so we're integrating this again, which is just qt times du. So we need to take the derivative of our u term. The derivative of this thing is just negative r times e to the negative rt dt. Okay, so this thing, we're going to evaluate at cap t and 0. So we have e to the negative r cap t q cap t. The minus, we have to minus this whole thing evaluated at 0. But we're going to assume that q of 0 is just 0. That's pretty safe to assume. At the beginning of our rotation, we don't have any timber volume. So this thing evaluated at 0 is just 0. It's going to go away completely. So we can just worry about this piece now. We have a minus r in here that we can take out front. So this is going to become a plus. We can put it in r, 0 cap t, q t e to the negative rt dt. Okay, so and remember we had a gamma in front of this thing up here. So that's our first term. So we can rewrite everything down here. We can notice that this thing and this thing, the other term that we didn't yet work with, are actually the same. And we have this one's positive, this one's negative. So these two things actually cancel out completely. And all we're left with is this thing, which remember, we still have our gamma times r times this integral. Okay, so this is our simplified A cap t equation for our carbon payment and fee policy. And all right, so this is the thing, the simplified equation that we just derived. Since all the terms in this equation are positive, we know that the net present value of the carbon payment and fee policy is positive to the landowner. But what it's suggesting is that the landowner has to invest all of their carbon payments that they receive over time at the interest rate R, or at the discount rate, which is, you know, the risk-free interest rate. And by the end, all they're getting back, which is what this equation represents, is the interest on those carbon payments. So if they don't invest the carbon payments over time, by the end, they'll end up with nothing. It is important to note that we made an assumption here that V is constant. If V is changing over time, if we had an increasing carbon price over time, it is possible that the landowner could have a negative amenity value over time if V is increasing faster than the interest rate. Then they wouldn't be able to make enough interest on their carbon payments to pay off the carbon fee when they harvest. But the main idea for the assumptions we've made is that a constant carbon incentive and fee policy will increase the net present value of a forest land use, and therefore will be positive for storing more forest carbon on the extensive margin. So that's the main idea there. Now we want to think about what would the effect of this carbon payment and fee policy be on the intensive margin. So we want to understand what's the effect of this policy on the rotation length. And to do that, we're going to look at the first order condition in our amenity setting. So this is the marginal benefit here, the left-hand side of our first order condition, marginal benefit of waiting to harvest, which is our timber value of waiting to harvest, plus our amenity value of waiting to harvest, has to be equal to not waiting to harvest. Our marginal cost of waiting is that if we harvested now and invested our revenue from the timber harvest at rate R, we could get this little additional amount of revenue. And if we harvested now, we could also just sell the land for its net present value, which is what this term is, and get that interest rate R as well. So that's just a repetition of the first order condition that we've been talking about for this whole module. And what we want to know is, given how we've defined AT, which is showing up here now, and it's also showing up in our net present value equation as well, how have we impacted the marginal benefit of waiting versus the marginal cost of waiting? And we're going to see if we can find some definitive truth of how we've defined this amenity value, how it's impacted marginal benefits and marginal costs. So what I've done here is I've just simplified this equation to what we've added to the marginal benefit side, which is just this thing. All we did to the marginal benefit side compared to a no amenity setting is add little a cap t. And on the marginal cost side, we've added this thing times R and this thing times R. So that's all I have on the right-hand side. And what we want to know is, did we add more to the marginal benefit side than to the marginal cost side? If we added more to the marginal benefit side, then we know that we had the effect of increasing the rotation length, because so now we haven't yet exhausted the marginal benefits of waiting. So this is what we want to try to see, if we've actually added more to the marginal benefit side than to the marginal cost. All right, so how do we figure out if that's what we've actually done? We're going to try to manipulate this expression until we get to something that we know is true. And then we will say that, yes, this thing is also true. Okay, so how do we do that? We can just rewrite this don't have my eraser at the ready. So we can take out our AT, since that shows up twice. We can simplify this thing a little bit by making this thing look like this, right? That's just 1 plus 1 over E RT minus 1. And so the numerator will just simplify to ERT over ERT minus 1. And that, if we divide the top and bottom by E to the RT, we'll get 1 over, oh, come on. 1, oh no, my guy is sad. Where is he now? Okay, 1 minus E to the negative RT. Okay, so now this thing is this, a little bit simpler. Okay, now, so let's just rewrite that. Divided by 1 minus E. Okay, now let's write out what each of these things actually are. So on the left-hand side, we have R gamma Q cap T. That's how we're defining our little A, right? And then this thing, our AT is that. Is that everything? And so we have an R and a gamma on each side that we can cancel out. And then this thing, we're going to, again, integrate by parts. So I suggest you try to do that yourself, given the integrate by parts example that I just went through. This time, we're going to set U equal to QT and dV equal to E negative to the RT dt. Okay, so that's what we're going to do there. If we do that, then we're going to be left with this thing. Plus so that's Q prime T, so that's the derivative of QT. So go through that exercise yourself that you can get this from integrating by parts. Now we have Q cap T on both sides here. We can bring this one over here. And actually, our R goes away as well, because when we integrate this by parts, we end up with a 1 over R. So our R is going to go away. Sorry, this is getting a little messy. When we bring this term over here, we'll end up with Q cap T times 1 plus E to the negative R cap T over 1 minus E to the negative R cap T. This, again, we can simplify just how I did before, simplifying this type of expression so that it will equal Q cap T times 1 over 1 minus E to the negative RT. Keep in mind, we're trying to prove this, so keeping the question mark involved is always good. And this thing, now we've just now all we have left on this side is the integral Q prime T dt. And now we can cancel out these terms. And what we're left with is something that we know is true. Right? Because we know that Q cap T is just equal to 0 to T, integrating the derivative of QT from 0 to T. That's exactly what cap T is. But on this right-hand side, we're multiplying the derivative of QT times this thing, which is always going to be less than or equal to 1. It'll be 1 if R is 0, but for any positive interest rate or discount rate, this thing will be less than 1. And so we're guaranteed for this Q cap T to be larger than this equation, than this term. So that's good. What we've shown is that by including a carbon payment and fee for the landowner, we have inevitably increased the marginal benefit of waiting to harvest. So that means we know that our optimal rotation rate has increased from the case where we don't include any amenity values at all. And we've shown that that holds no matter what level of carbon price we set, assuming as long as it stays constant over time. And we've shown that it doesn't even matter how we've specified our timber volume function. So a pretty solid result. We've definitely increased the value of forests on the extensive margin, and we've definitely increased the amount of carbon on the intensive margin. So this carbon fee and payment approach seems to be pretty powerful. You're going to have some problems relating to these questions and derivations on the homework, I think. And so I'd love to talk more about this stuff with you guys if you're interested, and hopefully this was useful.